in chapter 8.1, and it's an introduction to functions. So we're going to start by first finding the domain and range of a relation. Well, definition. A relation is any set of ordered pairs. So it's a set. Remember, set notation are these curly brackets. And inside that set, I can have any ordered pair. So there's an ordered pair 2, 5. Here's another one, -3, 9. This would be an example of a relation. Any set of ordered pairs. The set of all first component of the ordered pairs is called the domain of the relation. So the domain is really corresponding to the x values. So if you have an ordered pair written as x, y, well, who's the first component? It's x, so the domain is the x values. And the set of all second components is the range. So again, you have your ordered pair x, y. So the range is talking about the y values. So the domain would be the x values and the range would be the y values. For my example up here, well, what's the domain? It would be -3, 2. So the x's are -3 and 2, and we just put them in order. And the range would be 5, 9, the y values. So let's find the domain of this relation. So the domain is all of the x values. Remember, the x value is the first component of your ordered pair. So we have 0, 10, 20, 30, 38. 0, 10, 20, 30, 38. So the domain is a set of all x values, and the range is a set of all the y values. What do we have here? 9.1, 6.7, 10.7, 13.2, and then 19.6. Alright, second objective. Now we want to determine whether a relation is a function. So remember, a relation is any set of ordered pairs. Now the question is it a function? So let's go through our definition. I'm looking right here, and it says a function is a correspondence from a first set, called the domain, to a second set, called the range, such that each element in the domain corresponds to exactly one element in the range. So each element in the domain corresponds to exactly one element in the range. What's that basically saying? Each x corresponds to exactly one y. Each x corresponds to exactly one y. If that is true, then that relation is a function. A trick is to look for repeats in x. Okay, so repeats in the x values. If there are repeats in the x values, then not a function. And if there are no repeats in the x values, then you can say yes, a function. Now notice here we're only talking about the x values. I can have repeats in my y's and it will still be considered a function. So the definition says each x corresponds to exactly one y. If there are no repeats in your x values, then yes, you can say that relation is a function. If there are repeats in your x values, then you have to say that relation is not a function. Here's an example. They have the relation, and it's a set of ordered pairs 1, 2, 2, 3, 3, 5, and 4, 3. And they say, note that the y value 3 is the image of two x values. So what do you see here? I see 2 go into 3 and 4 go into 3. Now the question is this a relation? Is this relation a function? And the answer would be yes. You are allowed to have repeats in your y's. Do you see repeats in the x? Well, I got 1, 2, 3, 4. No repeats, therefore it is a function. All right, let's look at an example. It says determine whether the following is a function. So here is a mapping. The first map, which is purple or lavender, is for the domain, and the second, I'm going to call it orange, is for the range. So here they're telling me 1 maps to flute, 2 maps to drums, 3 goes to guitar, and 4 goes to drums. Now, do you see any repeats in your domain? For example, this is how a repeat would look. Well, 4 could map to drums as well as map to flute. That would be an example of a repeat, and we say it wouldn't be a function, right? Now the question is, do we see any repeats? We do not, so no repeats in the domain. Therefore, this relation is a function. Notice that we do have repeats in the range though, right? We see that 2 goes to drums as well as 4 goes to drums. Is it still a function? Yes, because you can have repeats in your range, just not in your domain. All right, another example. So we see 3 corresponds or maps to moss, 8 maps to ants, 9 maps to ants, as well to moss. So what do we see happening here with the 9? It's being repeated. So we have repeats in the domain. So what does that say? Not a function. Each element in my domain must map to only one element in my range. 9 maps to ants as well to moths. Therefore, this is not a function. Okay, now it says determine whether each relation is a function. We have 3 to work through. So the first one includes the points 2, 3, 4, 5, 6, 5, 9, 10. So let's automatically look at the x values. I'm going to circle them. 2, 4, 6, 9. Do we see any repeats? No, therefore it is a function. It does not matter what's happening to the y's, right? It's the x value, it's your domain. Let's look at this one. 1, 2, 3, 3, 6, 8, 1, 10. So automatically, do you see a repeat? 1 as well as 1. 1 maps to 2 and 1 maps to 10. Therefore, this is not a function. The last one, again, we have the points 1, 5, 4, 5, 2, 5, and 3, 5. Let's circle our x values. 1, 4, 2, 3. Do you see any repeats in your x values? The answer would be no, therefore this is a function. Again, it does not matter if I have repeats in my y's. All right, objective 3, evaluating a function. So functions are usually given in terms of equations rather than Functions are usually given in terms of equations rather than as sets of ordered pairs. For example, consider the function y equals 2x minus 3. This is an equation and it is also a function. For each value of x, there is only one and only one value of y. So let's say I chose x to be 3. What I would do is plug it in and figure out what is y. So y in that case would also have been 3. What does it say if I let x be 2? Then y would be 1. So for each x, there is only one y. The variable x is called the independent variable, and the variable y is called the dependent variable. X is independent because you choose it to be any value you want. Y is dependent because it depends on the value of x that you've chosen. Okay, more definitions. I'm going to basically start right here. When an equation represents a function, the function is often named as a letter such as f, g, h, capital F, capital G, capital H. They all mean one thing, which is function. Now realize that the variable y is also a function. So f, g, h, capital F, capital G, capital H, they also mean the same thing as saying y. When you see the function notation is written as f parentheses x close parentheses, and you read it as f of x or f at x. Do not make the mistake thinking that this parentheses means times. It does not mean times. It literally means f of x. F is a function of x. Now let's find some indicated function values. So we have the function f of x equals negative 4 x to the third power minus 2x plus 7. And we need to find f of 3. So notice what's in the parentheses here and what originally was in the parentheses. Originally we started with an x. Now we have a 3. So what does that tell us? Everywhere that we see an x here, we're going to replace it with a 3. So f of 3 is going to be negative 4, and then you have 3 raised to the third power minus 2 times 3 plus 7. So what is that? That is negative 4 times 27 minus 6 plus 7 which should come out to be negative 107. So notice what is different inside the parentheses? The 3. So what are you going to do with the x? Everywhere you see an x, you're going to replace it and put 3. Now we have q of negative 4. This time, q is not a function of x, it is actually a function of z. So what's originally inside the parentheses? A z. And what is now inside the parentheses? A negative 4. So everywhere we see a z here, we're going to replace it with negative 4. So we have q of negative 4 equals 3 times negative 4 squared. But remember it's negative, so be careful. Make sure you're using parentheses. Minus 6 times negative 4 to the 5th power. Now let's calculate what this will be. So 3 times negative 4 squared minus 6 times negative 4 raised to the 5th power, which is 6,192. Now let's find f of 6. This time our function is f of x equals 4x plus 5. Well, again, f of 6 means everywhere we see an x, we're going to have to put a 6. So here we have 24 plus 5, which is 29. G of negative 5, well, g of x is equal to 3 times x squared minus 10. What's replacing the x? Negative 5. So we're going to do that. G of negative 5 will be equal to 3 times negative 5, whole thing squared, minus 10, which is going to come out to be 65. And then last one, f of a plus h, for f of x equals 6x plus 9. Now this one's different. Inside parentheses is normally x, because we're a function of x, right? But this time, what's different inside the parentheses? A plus h. So everywhere we see an x, what do we need to do? Replace it with a plus h. So f of a plus h is going to be equal to 6 times a plus h, make sure you're using parentheses, plus 9, and then you can simplify this to be 6a plus 6h plus 9. You cannot combine these because they are not like terms. Okay, so now we have a table, and it says function g is defined by the following table. And it says find g of 1. Now, if you notice, it says g of x up here. And when we see g of 1, what has replaced the x? 1. So you're going to start by first finding where does x equal 1? It's right here. And then the second thing is, what is g of 1 then? So you're going to scroll over to the g column. And what is g of 1? It's 0. So g of 1 is equal to 0. Now, we still have a table for g. And it says find x such that g of x is equal to 3. So this time they gave us the actual g of x, right? So here's our g of x column. Let's find where it is 3. It is 3 here. And they want us to find x. So go back over to the x column. So what is x when g of x is equal to 3? X is equal to 0. Okay, so this concludes our video for chapter 8.1. Please email me if you have any questions.